Hello, a very good afternoon, everyone. I am Geeta, and it's my pleasure to welcome you all on behalf of eMobility Plus and First View Group to today's webinar on designing efficient electric motors with COMSOL. As we all know, electric motors power the technologies that keep our industries, infrastructure, and everyday lives moving. So, from industrial machinery and automation systems to electric vehicles, appliances, and renewable energy technologies, motors are the heart of innovation across countless sectors. As demand continues to grow for higher efficiency, better performance, and a faster product development, simulation has become an essential part of modern motor design and engineering. Today's webinar will demonstrate how COMSOL Multiphysics helps engineers in modeling, analyze, and optimize electric machines with greater accuracy and confidence, enabling smarter design decisions and concept through validation. Whether you're working on industrial systems, electric mobility, automation, energy technologies, or advanced electromechanical products, this session will help valuable insights and will provide you with a lot of insights that you can apply directly to your work. So, before we begin, I would like to extend our sincere thanks to our technology partner, COMSOL, for today's webinar. A renowned for leadership in multi-physics simulation, COMSOL has helped engineers and innovators across industries accelerate product development, optimize performance, and gain deeper insights into complex engineering systems. So we appreciate their partnership and look forward to a very valuable perspective they will share with us today and their continued support and collaboration in making today's session possible. A quick update for you, audience. Please feel free to post your questions throughout the webinar in the Q&A box. We will address as many questions as possible during the live Q&A session at the end of the presentation. And we will be launching interactive polls during the presentation, and we encourage you all kindly to participate in them. Moving ahead, it is my pleasure to introduce our speaker for today's session. We are so delighted to welcome Ms. Kavita K., Senior Application Specialist at COMSOL Multiphysics Private Limited. Ms. Kavita earned her master's degree from the Cochin University of Science and Technology and has previously contributed to research projects at the Raman Research Institute. Her expertise spans electromagnetics and MEMS applications, and she currently serves as team lead for the electromagnetics team as well as a senior specialist helping organizations solve complex engineering challenges through multiphysics simulations. We are delighted to have her with us today. In today's session, Ms. Kavita will demonstrate how COMSOL Multiphysics and the AC/DC module can be used to model, stimulate, and optimize a wide range of electric machines, including both radial flux and axial flux designs. With that, it is my pleasure to hand over the session to our speaker, Ms. Kavita. The stage is all yours. Hello, Ms. Kavita. Ms. Kavita, we are ready to start the presentation.
Yeah. Thank you, Geeta. So welcome everyone. So thank you for joining for today's webinar on the topic of designing efficient electric motors with COMSOL Multiphysics. So in this webinar, we will primarily demonstrate, we'll demonstrate how COMSOL Multiphysics helps engineers and organizations to model, analyze, and optimize electric motors efficiently before you build your physical prototypes. You will see how simulation can provide valuable insights into motor performance, identify design improvements early in the development cycle, and you can support faster and more informed engineering decisions beforehand. And also, I would promise that by the end of session, you will have a better understanding of how multiphysics simulation can be integrated into your design workflow to improve your overall product performance, to shorten the development timelines and reduce the overall project cost. So thank you for taking time to join us today for this topic. We'll move ahead. So to start with, I would like to start by introducing COMSOL Multiphysics Simulation Platform. So it is a unified environment where you can combine different engineering physics streams to simulate a multiphysics product. So COMSOL has solutions to simulate several single physics phenomena like electromagnetics, fluid flow problems, structural mechanics, chemical engineering problems, acoustic problems, and so. Apart from that, COMSOL is a unified environment where you can couple two or more physics together. You can couple two or more physics to simulate a multiphysics application. And there is no limit on how many physics that you can couple. So you can couple a number of physics to simulate a real-time product. So for motor design, primarily this is very important because motor involves electromagnetics, heat transfer, mainly to compute the losses or to produce the efficiency map or temperature map, and structural mechanics physics to assess the vibrations that are caused because of the rotating machinery. And sometimes you might be interested in evaluating the radiated noise out from the machinery as well. So COMSOL is a unified platform where you can couple your electromagnetic physics with heat transfer, structural mechanics, and acoustics, and solve for all the characteristic performances of a single operating machinery in a single GUI. And the workflow that you are going to use for different physics is going to remain the same. So the engineer who sets up the electromagnetic physics, so it would be more easier and efficient for the same engineer to set up the heat transfer, structural mechanics, or acoustic physics as well to evaluate the performance of a product from multiple dimensions or from multiple physics point of view. Before moving on to the further part of the session, so I would request our host to launch a poll question here. So with respect to this poll question, so we would want to understand whether you are a regular user of simulation tools or you are evaluating simulation tools for any of your ongoing or upcoming project, or you are attending the session out of your personal interest, or you're very new to multiphysics simulation. I would request the attendees to kindly take time to answer the poll question here. Thank you for answering the poll question. Thank you, host, for posting the poll question.
Thank you.
So to move ahead, we'll start with this slide here. So here you can see a picture of what COMSOL provides. What are the different features that COMSOL provides to model electrical machines? So there exists a number of dedicated features set within COMSOL Multiphysics to model motors. One of the basic and important feature is the coil feature, which helps you to model the phases of a stator, for instance. This can be either a solid conductor or it can be a multi-turn coil. And when we talk about a multi-turn coil, so it is essentially a stranded coil, as you can see in this picture. So this is the coil winding on your stator slot. So if you look at this multi-turn coil, so in this case, we assume that the skin depth is usually much larger than the actual coil. So you can assume a homogenized current density here for which you have a feature called homogenized multi-turn coil feature available within COMSOL to model the coils efficiently. COMSOL also supports laminated iron modeling with respect to eddy current losses. So depending on if you are in frequency domain, working in frequency domain or in time domain, you can either use a magnetic loss formulation or a hysteresis model respectively in order to save computational time. And to save computational time for very large machineries, you also have sector modeling feature and symmetry conditions available as well with the tool. And there is also feature to perform torque calculations as well. And in order to support all kind of motor models, COMSOL also provides many different magnetic material models. So you can define the hard and soft magnetic materials. You can define magnetic saturation or anisotropic material properties. You can define magnetic loss, and you can also define your material properties to be a function of temperature as well. So your copper, so let me say, for example, here the copper can be represented as a linearized resistivity, or the temperature dependent material properties can be specified for the conductive parts, as well as it even for your magnet. So the remnant flux density can be a function of temperature as well. When talking about different types of machinery that you can simulate with COMSOL, so you can model radial flux missions, so you can model it in 2D, 2.5D or 3D as well. So in case if you want to take into account the end effects or flux leakage in skewed rotor geometries, etc. So you can also switch to 3D modeling. You can also model axial flux motors and linear motors as well in COMSOL. So when we talk about axial flux motors, so where the rotor and stator both are disc shape and the flux flows axially. So here inherently the geometry is 3D in nature, and where we need to consider modeling the motor model completely in 3D. So COMSOL can handle simulation of these missions as well. So linear motor is another category which are used in semiconductor equipment or factory automation systems. So these kind of motors can be modeled in 2D, taking the periodic boundary conditions to approximate a very long motor without modeling its full length. So you can model only a unit section, and you can use periodic boundary conditions to approximate a long motor. So here, in this diagram that you see here, so this is a conceptual heart representing the beauty of a multiphysics platform. So the arrows you see here, every arrow represents a physical coupling that signifies the real motor performance. So to start with at the center, so we are interested in evaluating the electromagnetic fields or assessing the performance of an electrical machine. So these fields produce forces on the stator. So we couple the electromagnetic fields, basically the forces, to structural mechanics physics, okay, and to assess the vibrations, etc. And the vibrating structure can be coupled with acoustic physics to assess the radiated noise out from the rotating machinery. Further, if we move towards the right side of this particular picture, so from the electromagnetic losses, so you can also evaluate like the core loss or the ohmic loss, etc., would be the source of heat to the heat transfer physics to assess the temperature distribution. And once we compute the temperature changes can be then fed back to the electromagnetic material properties. So you have a unidirectional coupling as an option or a bidirectional coupling, so where electromagnetic heating has to be simulated, as well as the material properties are again a function of temperature, can be taken care as well. Further, the heat transfer physics, so the electromagnetics along with heat transfer can be coupled with computational fluid dynamics in case if you want to solve for conjugate heat transfer to assess for the ways to cool your device. You can also simulate for magnetostriction effects as well. So when coupling with structural mechanics. Okay. So all of these couplings for this rotating machinery exist in a single GUI, and all these couplings can be present within a single model. in a single GUI, where you can derive the complete working scenario of a motor from all perspectives. So you can assess the product performance not only from electromagnetics point of view, but structural integrity, or to have minimized acoustic noise radiated out from the device, as well as handling the temperature effects out from the device as well. Further, you can also optimize the design. And when you're going to perform optimization, so we would talk about the optimization in further slides. So your optimization can be a multi-physics optimization. So when we are going to couple two or more physics, we would be optimizing it with respect to multiple objectives in a multi-physics scenario. So I need to optimize such that I take care that I minimize the mass or minimize the mass of the product, as well as I need to take care of its electromagnetic performance as well, or I can also minimize the temperature at the same time. So you can do a multi-physics, multi-objective optimization within COMSOL. Moving ahead, we have a user story here from Volkswagen Castle. So this is a case study which shows how simulation looks like at an industrial scale. So here the Volkswagen Castle, they produce 150 electric and 300 hybrid drives per day. So their simulation experts build detailed COMSOL models of rotor lamination strength, but the experts cannot be always in the loop for every design decision made by every engineer at the plant. So the solution that they came up with is to have an app built out from a COMSOL model. So COMSOL has a capability to derive an app out from a model. So they had the solution to build an app using COMSOL's application builder. So the expert builds and validates the physics models once, and then it will be turned to a user-friendly app. So any engineer now can input their rotor dimension and get a structural analysis results in minutes. So no simulation expertise would be required. A detailed expertise may not be required, and the result is the result here is an automated evaluation. So you have fewer physical prototypes, faster design cycle, and you can assess the product quality in a better way. So this is how simulation expertise scales across an organization. So by having the app building platform or generating a simplified GUI environment to modify the designs of a model is available within COMSOL using the application builder. So moving on, here we'll talk about the losses. So losses determine both the efficiency and the thermal load. So evaluating the losses right is very critical. So COMSOL offers features to calculate Steinmetz or Bertolli loss, which considers the magnetic and electric losses within iron. So this empirical formula which you see here, so this is for evaluating the Steinmetz loss based on Steinmetz loss model to evaluate the losses in the iron. So this empirical formula for the loss that you see in this picture, so it is widely used in industrial standards. So it works on constants given by manufacturer, and then this formula is scaled by local fields and the local magnetic flux density obtained from simulation. So since this equation operates in frequency domain, so first we apply a fast Fourier transformation to obtain average cyclic losses, so which is then further fed to a thermal simulation. And for obtaining the ohmic losses, so here you need to change just this drop-down arrow, so option, so where you can switch to evaluating the ohmic losses as well. And for the iron loss, apart from Steinmetz or Bertolli loss model, so you can also define a user-defined loss model as well. So as we talked about loss, and they are going to be a source of heat for the thermal simulations or heat transfer simulations, the temperature dependency of the material properties also plays an important factor to assess the thermal performance of a device. So in order to perform any thermal simulation, we require to define a temperature dependency. So this can be done in two ways. The first way is to do a one-way coupling where your losses are incorporated as a heat source in the heat transfer physics. and the resulting temperature fields can be visualized. The second solution is to do a two-way coupling where a feedback exists. So the salt temperature can be fed back to the electrical problem. So in many cases, this is very important because the electrical parameters are also a function of temperature. For example, if we take the case of copper here, so which is defined for the coil feature. So we have here the domain coil feature. So defining the phases, different phases. So now if we take the conductivity of the copper, so here the copper conductivity is represented in terms of, or the whatever is the conducting material that you are going to use for the coil. So the conduction model can also be linearized resistivity here. So which is dependent on the average coil temperature in this case. Also, you can also have the dependence of temperature for remnant flux density as well. So in this way, your material properties are a function of temperature. And when you solve a coupled problem, so the electromagnetic physics or the rotating machinery physics along with heat transfer, so as the temperature changes over time, the effect of temperature, so with affecting the material properties are also incorporated, and you would be able to assess the realistic, produce the realistic temperature maps or efficiency map or evaluate the temperature distribution of the device, incorporating the temperature dependency of the materials as well. Further, you also have magnetomechanical coupling available within COMSOL. So that which helps you to connect basically the electromagnetic physics with the structural physics. So here the archeotorque calculation feature. So this integrates the Maxwell stress tensor over surface in the air gap, giving rotor torque directly without any mesh dependency. You also have the magnetic elastic interaction multiphysics interface. So this handles the full bidirectional coupling between electromagnetic forces, how the electromagnetic forces drive the structural deformation, and that deformation changes the geometry of the electromagnetic domain, and further you continue your electromagnetic simulation. So you have a bidirectional coupling between the magnetic field physics that you are going to solve from your the machinery to the structural mechanics physics. So this is important for rotor eccentricity study, where even a slight misalignment causes unbalanced magnetic pull. So a force will be generated that tends to pull the rotor further out of alignment, so potentially leading to any failure. Okay, so these kind of analysis can be performed within COMSOL. Further, you can also couple your rotating machinery interface with rigid body interaction, which is a lighter version for studying rotor dynamics and bearing loads without requiring full stress analysis of the complete device. Before moving further ahead, so here we would like to launch another poll question. So I would request the host to launch the next poll question. So this is mainly to understand the area of interest of today's attendees. So whether you are interested in modeling induction motors or BLDC or permanent magnet motors, or you are interested in simulating axial flux motors, or you are interested in multiphysics analysis for motors, or if it is any other aspects that you are interested in with respect to COMSOL multiphysics, you can type it in the questions tab as well. I would request the attendees to take time in answering this poll question. So this helps us to understand the background of today's attendees, on which domain or areas they are interested in. So to simulate these different variants of motors or multiphysics analysis for motors. Thank you for answering the poll question. Moving further, this model which you see here, this example model demonstrates motor misalignment. So COMSOL can also do motor vibration analysis. So vibrations here in this particular example, it is caused due to eccentricity, which is the misalignment between the rotor and the stator. It is not that you can only display these stresses in the housing, but you could also overlap the animation with the rotor velocity as well, as indicated here in the middle picture here. So here in this model, so when the rotor center do not coincide exactly with the stator center, so the air gap becomes non-uniform around the circumference. And this non-uniform air gap means unbalanced electromagnetic forces. So there is a net lateral force on the rotor called unbalanced magnetic pull. And this force will excite vibration modes of the motor casing, and it increases the bearing loads as well. So this simulation couples 2D electromagnetic forces to a 3D structural model of the motor housing. So the key outputs that we evaluate here are the stress distribution in the housing and the rotor orbit in the bearings, so which feed directly into the bearing fatigue life calculations, or to further predict the noise vibration harmony, like NVH predictions can also be further assessed. So the structural acceleration out in this casing can be used as the source to assess the radiated noise out from the device further. So to move on, the time periodic electromagnetics. So it is one of a game-changing capability for motor engineers available within COMSOL. So when we look at the traditional transient simulation, so they start from rest and steps forward in time until the motor reaches a periodic steady state. So when we go with motors with many electrical cycles before steady state, this can take thousands of time steps. The time periodic approach directly imposes that solution is periodic in time, and it will solve for all time frames simultaneously. So we skip straight to steady state and we solve in one go. So this is particularly transformative and very essential when we are doing parametric studies or to evaluate the efficiency map and temperature map. So where we would perform parametric studies. And it can be also very useful in cases where we couple with other physics like heat transfer physics or structural mechanics physics to assess the vibrations. And also when we are going to perform optimization, so topology optimization or any objective based on the fast Fourier transform. So in those scenarios as well, the time periodic analysis for the rotating machinery is very useful and efficient. And it is in general can be used for any model that requires many cycles to reach the steady state. So there would be a dramatic reduction in the total computation time. So moving on, when we are talking about the temperature distribution or thermal analysis of motors, so once we have the temperature field, you can also create temperature map or efficiency map as shown here. So you can compare how the produced torque with the actual speed of the rotor, how the torque changes with actual speed of the rotor and the temperature together. So the efficiency map, they are most important deliverables in motor development, and they show how motor efficiency across entire operating range of speed and torque exist. So with traditional transient analysis, each point running for each time step requires longer time to reach the steady state. So where you use the time periodic approach, so where the electromagnetics and the heat transfer physics, they are solved together as a stationary couple problem. And here the solver uses a previous operating point solution as a starting guess. And you can derive the complete efficiency map, which earlier used to take a lot of time. With traditional transient simulation can be generated in a few hours using the time periodic approach. So the time periodic approach also extends across the full multiphysics chain. It is not only for coupling the electromagnetic forces with heat transfer physics, but also like you can couple across structural mechanics and further assess the radiated noise out from the device as well. So for thermal analysis, you couple to stationary heat transfer for nominal operating conditions, or you couple it to time-dependent heat transfers for studying how temperature evolves during a slow speed ramp up. So the magnetic field harmonics are extracted and they are fed directly to your Steinmetz heat source. So no separate post-processing would be required when you are going to solve a coupled multiphysics problem for rotating machinery along with heat transfer. And when we talk about vibroacoustics, mainly the time periodic electromagnetic solver, it extracts the harmonic force density at each operating frequency automatically. And these forces are then coupled one way to a frequency domain structural and acoustic analysis. So the result is what we see here in this diagram, the picture at the top right corner. So where you can have the sound pressure level and vibration predictions at any number of operating points, all from a single integrated study. So this is what we see here as a Campbell diagram. So you can have the shaft speed frequency, like the harmonic responses for different shaft speed. And also you can evaluate the sound pressure level as well. So moving on, so here we are going to talk about one another very important topic where COMSOL plays a major role. So optimization is where you are going to move from the analysis of motors to improvement of your existing design. So the topology optimization example, which is shown here on this slide, illustrates why multiphysics optimization is very important. So if you optimize the rotor topology purely for magnetic performance, you get a design that maximizes your flux, but it can be structurally weak here. So if you optimize purely for structural strength, as shown in the left diagram, so if you optimize purely for structural strength, you get a strong, like structurally which passes the structural integrity test, but magnetically it can be an insufficient design. So the multiphysics simulation based optimization is going to balance both simultaneously. So the results that we see here in the bottom picture here for the optimization study. So this talks about the multiphysics multi-objective optimization. So the results here from this optimization, they are very impressive compared to the starting design of this particular motor model. The optimized motor here achieves 8% more average torque, 2.5 times less torque ripple, 38% less iron mass, and 14% lower maximum stress, all at the same time, because you do a multiphysics simulation based optimization. So it is multiphysics in nature, and you are going to have multiple objectives that has to be met at the same time. So this is only achievable with a gradient based multiphysics optimizer. Further, you also have parameter optimization. So this is most accessible at the starting point of your design. So you define any geometric or material parameters as your control variables, and you specify an objective function. The objective function can be to maximize the average torque, and you can also set constraints like maximum stress or minimum efficiency, etc. The optimizer will iterate running the model at each control parameter, and it adjusts the parameters to achieve your objective function. So this example here with the parameter optimization, so achieves, say in this particular model, achieves more 10% torque increase while keeping the winding loss, magnet volume, and the rotor stress at their original levels. Okay, so this is on parameter optimization. You can also perform shape optimization in COMSOL. So shape optimization is also a powerful tool because it has more freedom. Instead of adjusting a few discrete dimensions, it continuously deforms the boundary of the geometry. So here you can see the rotor geometry, the exterior boundary of the rotor. So you can see the optimized boundary or the shape at the periphery of the rotor. So here It continuously deforms the boundary of the geometry, the outer surface of the rotor, the boundary that faces the air gap. So this is basically the design variable. The boundary here is the design variable. The optimizer here used is gradient based. It computes the sensitivity of the objective function to small perturbations of every boundary point, and then moves the boundary in the direction of steepest improvement. So no remeshing is required. The result is like this results in a major reduction in the torque ripple in this particular example that you see here. So you have the initial torque. So the blue solid line is the initial ripple that you have, and the green colored solid line is the final design after shape optimization. So you have a large reduction in the torque ripple characteristics, which is a profile. So this profile or the shape is a profile that no human designer would find through intuition alone. So this is kind of an improvement that gradient-based shape optimization is uniquely good at delivering. So this is where the shape optimization plays a major role. So to summarize, COMSOL has three optimization techniques. So it can be parameter optimization in case if you are modifying geometrical parameters or material parameters to improve the performance. It can be shape optimization to optimize the shape at the boundaries of the geometry to achieve a certain performance, or it can be topology-based optimization as well. So where you want to reduce the material totem material, but as well as you want to have the maximum magnetic, like maximum performance with respect to electromagnetics point of view. So all three of these optimization techniques can be used as different stages of your design, and the optimization that we talk about, all three of them, so they work with full multiphysics model. So you optimize electromagnetic, thermal, structural, and acoustic performance together can be optimized simultaneously. Okay. Yeah. So now at this point, we will take a short demo session to highlight how you can use COMSOL Multiphysics platform to simulate motors. So this is the GUI that you would be taken to when you open the COMSOL simulation software for the first time. So you have two ways to navigate through. So you can use the model wizard button, which is the guided approach to choose the type of physics and the type of the study, etc. So let me click model wizard, and COMSOL prompts you to choose the space dimension, whether you would like to work in 3D or 2D, whether you want to model the motor in 2D or 3D. So you can select the space dimension, say I choose 2D. Then you can choose the type of the physics that you are interested in. So to model electric motors or generators, so COMSOL has the AC/DC module, and inside the AC/DC module, we have the section electromagnetics and mechanics. So here we have rotating machinery interfaces. Say, for example, let's choose rotating time periodic interface. So which is the most efficient interface to couple with other physics applications. So you can click add, and COMSOL adds this particular physics to our GUI. And say, for example, I understand at my initial stages that I would like to also add heat transfer physics as well to assess the temperature distribution or to evaluate the temperature map or efficiency map. So I can also add heat transfer in solids as well. Okay. So you can add two or more physics. So then you can click study, choose the type of the study that you are interested in, say time dependent or stationary, and click done. So once you click done, so COMSOL will take you with the setup of the initial settings that you have given as the input to the tool. So you have the physics already set up in the GUI, and you also have the type of study that you have chosen. So this is the graphical user interface of COMSOL. Towards the left, you have the model builder window, and at the top, you have the top ribbon tab. Both the model builder window and the top ribbon tab guides you through the modeling workflow. And the modeling workflow in COMSOL is as you start with defining parameters, geometrical parameters or input parameters, and then you start drawing your geometry using the available geometry primitives. And when we are going to talk about motors, So you also have a part library. So under geometry, you have parts and part libraries. So we can expand the AC/DC module. So you have already the part library for rotating machinery. So since we have chosen 2D here, so you can switch into the part library inside the 2D option, rotating machinery 2D. So it can be to, you can bring in the stator slot or the rotor geometry can be added to from the part library as well, or you can draw the user defined geometry, or you can import geometry from any CAD platform as well. So once you have the geometry, next you assign materials to your geometry, then you set up the physics. And once we set up the physics, so you can also add multiphysics coupling. So here, in case I have the iron losses, copper losses, and magnet losses, etc., as a source of heat to my heat transfer, so I'll include. So once you add two or more physics, COMSOL gives you an option to choose the multiphysics coupling that you want to establish between two physics. So you can choose that. And once your physics is and multiphysics is chosen, you mesh your geometry, then you compute your study and you visualize the results. So this is the workflow. So from top to bottom, you define parameters to assessing the result. And any option that you are going to choose in the model builder window, the upper and or the top ribbon tab, the settings appears here in the settings window. And towards the right, you have the graphics window to visualize the geometry or mesh and the results, etc. And at the bottom right corner, you have the information window that houses the progress information for your simulation or log information, or if you're evaluating any results in the form of a table, it appears here. So this is a quick overview about the GUI of COMSOL, and at this point, I'm directly taking you to the example. So this is an example of a motor, so where we are interested in deriving the efficiency map of this motor. So permanent magnet based motor. So here for the geometry, we have already the geometric parts of the geometry taken from the part library. So you can switch. So these parts are already taken from the part library. So if you go to the part library, as I had shown from the AC/DC module, rotating machinery 2D, so you can choose the rotor geometry and stator, parts for the stator as well. So once you click those parts and add it to the part library, so you have it them here in the global definitions. Then further in the geometry, you can just call that particular part that you are interested in. You can right click the geometry parts and you can call that particular part library and you define the geometry. And the parts are fully parameterized. So you can change the parameters of the models available in the part library for your stator slots or for your rotor geometry as well. So step by step, so you can design the rotor and further the stator slots or the geometries for the windings, etc. So can be defined here in the geometry section. So once the geometry is ready, so we assign materials to the geometry. So first the material that we have here is air. Then further the core, the iron part. So if we right click the materials, so you have two options to provide the material properties. One is you can add material from the library. So you can go to add material from the library AC/DC section. So in case if you are interested in magnetic materials, so we have a lot of options to specify the magnetic materials or magnets, basic materials available within for low frequency analysis as well, or in case any hard magnetic materials as well is available. So you can choose the materials from the part library, from the material library, or you can define a user-defined material by right-clicking material and clicking blank material option. Okay. So we have the soft iron defined here in these regions. So then we have the copper defined for the windings. And then you have the magnets defined here in these parts of the geometry. And here we have the steel defined. Yeah. Moving on to the physics setup. So here we have two physics added. So the prime objective of this particular motor analysis is to derive the efficiency map. So first we take the magnetic machinery rotating time periodic interface. So which is used to define the motor for defining the analysis of the motor. So here you can define the actual electrical frequency at which the motor is operating. The number of poles can be defined. So these options can be defined initially, and the out of plane thickness, since we are assessing in 2D, can be defined as well. And yeah, once the main physics is defined, so there are a few default boundary conditions and default domain conditions as well. And on top of it, so we add several other conditions. So on top of the default conditions that exist with this particular physics, so you add the other conditions. So first one is we define the rotating domain. Then you define the laminated core section. So to derive the loss characteristic, so you can specify the loss model. So whether it is Steinmetz based or Bertotti based loss model, or you can have a user defined loss model as well. Then you have the magnet section. So defined here using magnet feature. So all these options can be chosen by right clicking the physics. So you can choose you can configure your magnets, you configure your laminated core by clicking the laminated core option. And for your windings, so you choose the multi-phase winding option. Okay. So we have defined the magnets here. So you can specify the north, south poles of your magnets as well. Okay, and you can define the pattern in which your magnets are arranged, whether it's a circular pattern or linear pattern as well. So you can define that. And for the winding, so here we have used the multi-phase winding option. And when you are defining the windings, so if it is three-phase, so you can just choose this option, automatic three-phase, and automatically three phases are configured. So automatically. In case if you want to have any user defined configuration or end phase, so you can go for user defined configuration as well. Okay. So here you just need to, if it is three phase, you just need to specify automatic three phase, and you can specify what is your peak current, winding electrical frequency, the number of poles and number of slots, etc. So these information has to be given. So this is the setup for your time periodic interface for assessing the motor performance. And you have the heat transfer physics added to assess the temperature characteristics out from this device. So we specify here in what are the heat flux boundary conditions. And so this primarily solves for the conductive and convective heat transfer involved with this particular geometry setup. So in case if you have very thin structures, it has dedicated, instead of modeling them, the thickness of the geometry explicitly, you can just use thin layer boundary conditions to specify which boundaries are thin in nature. And you can specify the thermal conductivity available at that boundary instead of explicitly modeling a thin laminated section at the exterior to this particular geometry. So you can just specify a thin layer boundary condition. And heat flux boundary conditions are added to provide with the information about how the convective heat flux takes place and what based on the environment in which this particular motor sits in. So once the heat transfer and rotating machinery interface is configured, so you also add a multiphysics coupling electromagnetic heating, which couples your rotating machinery time periodic interface with heat transfer in solid. So your losses, electromagnetic losses, goes as a source of heat for heat transfer physics. So since when we solve it bidirectionally, when the temperature changes, so in case if you have your the conductivity of the bindings, etc., to be dependent on temperature, so they are as well taken care. So here we define copper. So copper's the material property as a function of temperature can be taken care as well. So yeah, in this way you can have a bidirectional coupling between your electromagnetic physics, the rotating machinery physics, along with your heat transfer physics. So once your physics setup is ready, so we mesh the geometry and we compute the study, set up the study and compute the study. So we'll go and look at the study where we do a bidirectional couple study. So here in this particular study where we are interested in deriving the efficiency map, so here first initially a parametric sweep is added to vary basically the speed of the shaft and the current, phase current. So both are varied to derive the characteristics of this motor to arrive at the efficiency map. So we vary the shaft speed and the phase current by adding a parametric sweep for those particular parameters. Then we do a couple stationary analysis. So since it is time periodic interface, all time frames are solved at once. So it's a stationary study. So your rotating machinery along with heat transfer physics and electromagnetic heating together, they are solved together in a coupled way, and you would be able to produce the magnetic flux density. You would be able to visualize different results. So you can visualize the magnetic flux density for different rotor speeds or different current, yeah, phase current. So you can visualize the magnetic flux density variation. You can visualize the temperature distribution. So again, the temperature distribution for different speeds and different uh, peak currents. So you can visualize the temperature distribution. You can also derive the efficiency map. So this is one of the important characteristics that we were talking about for having COMSOL simulation. So once you have a couple study, the effects of temperature are taken into account. So the material properties dependence on temperature will also be taken care, and you will be able to derive a much effective efficiency map in a single simulation, in a single GUI. So you use a single GUI to add heat transfer or further, say, structural mechanics or acoustic physics. All physics can be added in a single GUI to assess several multiphysics performance of a particular machinery. So you can also plot the electromagnetic losses as well. And yeah, so this is the part of the demo. I hope this demo gave you better insights of how COMSOL simulation environment sets up the multiphysics models for analysis of motors. Further, this is a slide which shows you an example of synchronous electric motor drive. So it is a great starting point if you want to explore these workflows by yourself. So this example is based on a real EV grade machine. So it is 240 kilowatts, 460 Newton meters, 48 stator slots with 8 rotor poles with the hairpin winding, and it also has segmented shaped magnets. So this model is also available for free download from the COMSOL application gallery. So through the motor tutorials series, so it comes with full documentation, step-by-step instruction, and all physics interfaces that we discussed today. So they are set up, and so you can explore this example at your convenient time to have an hands-on, like to understand and get insight about how COMSOL set up these kind of models, starting from 2D to 3D and a complete multiphysics simulations as well. So they are available with the motor tutorials series available under the COMSOL application gallery. So at this point, I would like to launch another poll question, the last poll question. So here we would like to know like whether you would be interested to connect with a COMSOL representative, or you would like to try out COMSOL for any of your project, both of the above, or yeah, none of the above. So you can, I would request the attendees to take time to answer this poll question. While you fill this poll question, so I hope this session had given you a clear picture of what is possible with COMSOL multiphysics simulation software to design electric drive systems. So whether your interest is going to be with just respect to electromagnetic design or thermal management of your electrical machineries, or to assess the vibrations out with your device or evaluate the acoustic performance, the workflows we have covered today, they are directly applicable to all real engineering problems. thank you for taking time to answer the poll question here. So let me summarize here with a key message that COMSOL Multiphysics provides you a complete tool set for electric motor engineering, not just the electromagnetics, but as we were talking about, to assess the torque, forces, thermal management, acoustic performance, or the structural integrity, and further design optimization. So you do an optimization for multiphysics simulation with multiple objectives in a single go, all in one integrated environment. So the capabilities that set COMSOL apart are time periodic electromagnetic analysis for fast efficiency map, and also the gradient based optimization with multiphysics simulations included for finding better designs efficiently. And I would also like to highlight the application builder for scaling the simulation capability across your entire organization. So thank you all for your time today. So you can also take the 2-week trial, and you can explore the application gallery that has everything that you would require to get started. So I'll be happy to take questions at this point.
So we have a few interesting questions here, Kavita. The first one is, can we couple a circuit with motor modeling?
Yes. Yeah. So you can couple electrical circuit with motor modeling as well. Say, for example, if you want to connect your motor with an inverter or any other electrical circuit, yes, you can couple it with an external electrical circuit. So COMSOL has an interface called electrical circuit interface. So you can couple between your finite element model with the electrical circuit interface.
Thank you. So we have next question from Abhay Arora. He says, can I hear the noise generated by motor? And how is COMSOL different from other tools with respect motor modeling and analysis?
Okay. So with regards to assessing the noise, yes. So as we had seen an example, so where we are assessing the structural analysis or the vibration analysis of the motor. So here, when we evaluate the stresses at the, say, for example, in the casing of this particular motor, the external casing. So for acoustic analysis or to evaluate the radiated noise, you just need what is the acceleration, structural acceleration at the casing, boundaries of the casing. So just we will include an air domain outside this uh, outer casing, and you would be using that acceleration, structural acceleration, as the source to assess the acoustic acoustic sound. So COMSOL has acoustic structure interaction multiphysics coupling. So that assesses how the deformations of this structure displaces the air outside, which generates the noise. So the acoustic structure interaction automatically evaluates the radiated noise. So assessing the radiated noise or producing the Campbell diagram plots that gives the idea of the radiated noise as well. So it is much straightforward and efficient to simulate using COMSOL. And on the query of how COMSOL is different from the other tools or where it stands ahead across other tools is mainly, as I had highlighted. One is the multiphysics simulation capability that it has. Second is the time periodic analysis that it has, where when you are doing simulations where it can take long time to achieve the steady state, or when you are performing multiphysics simulations, or when you're doing parametric studies, etc. So you can go for the time periodic approach where you can solve all time frames at once. And the third advantage, or how COMSOL stands ahead, is to perform optimization. So here the optimization, as I mentioned, is multi-physics based optimization. So you can couple multiple physics. So you can have, since we have multi-physics based optimization, you will have multiple objectives as well. So one objective might be to minimize the total mass of the structure, or to remove the material out from the geometry, whereas the other objective can be to maximize the magnetic performance And you can also have other objectives like to minimize the temperature or minimize the noise, etc. So you can have multiple objectives defined so that you can derive the best possible yeah, product from motor design point of view.
Thank you, Kavita. We have another question from Shruti. She's asking, can we perform co-simulation with heat transfer?
Yes, yes. So as we had seen, so this question mainly relates to the demo model that we had discussed. So where we were assessing the efficiency map or producing the efficiency map or temperature map. So you can always couple COMSOL simulations. So the as we had talked about, the rotating machinery physics simulations can be coupled with heat transfer physics. So it is done in a single platform. So it is done realistically, that is incorporating the actual physics of the rotating machinery, the losses computed from the rotating machinery directly going as the source for heat transfer, and also the effects of temperature affecting further the material properties. So it's a bidirectional study. So you can do the co-simulation. So coupling the rotating machinery with any rotating machinery with heat transfer physics in a single GUI.
Thank you. So the next question is for Mr. Roberto. Says the stationary solver generally uses T equal O in the general parameters to converge. Is that correct? And how do you use the stationary solution with time-dependent PDE physics, specifically in the context of superconductors?
Okay. So when we talk about motor modeling, so if we talk about in terms of motor perspective, so here when we are going to, so it depends on the type of the physics interface or the physics formulation that we are going to use, and it's going to also depend on the application as well. So when we are talking about motors, so if it is a multiphysics simulation of motors, always we prefer choosing the time periodic interface where you can solve all time frames at once, and so there it would be efficient to couple with heat transfer physics. But if we use a traditional transient approach, so without the time periodic analysis, so then I need to use a time dependent study, so where it would take time for to achieve the steady state, whereas you would be solving the uh, rotating machinery along with heat transfer together in a single go. So you can do a time dependent simulation as well, which might take longer times. Whereas this particular interface does it at a short duration with this approach. So when we talk in the context of superconductor, I think this particular, if it is for the specific application areas of interest, so we can get in touch through COMSOL support as well to answer you in a better way so that we can have better clarity on your application area of interest. So then we would be able to provide you the right solutions there. So for other application specific queries, I would request you to also write down the queries to COMSOL support. So we would get in touch to answer the query from the application point of view.
Thank you. We have another question from Abhijit. Says one slide showed anisotropy modeling. It's possible for magnetic material? And can you show which options or parameters are to be used for modeling directional permeability in lamination?
Okay. Yeah, I didn't get the complete question. So you can read out the question as well once more.
Okay, so it says the one slide showed anisotropy modeling.
Okay,
So
and
is it possible for magnetic material? And can you show which options or parameters are to be used for modeling directional permeability in lamination?
okay, sure. Yeah. So when talking about the material properties, so I hope the screen is still visible. So when we talk about magnetic materials, yeah. So depending upon your application, so in case if you want to include any anisotropy properties based on the material, it is going to be again based on the material. So any material that you take, so whether it is going to be conductive material properties or say, for example, any other material properties where in case the anisotropy plays a role, so you can change the material model. So you always have the option to change. So whenever you are defining a particular material, say laminated core, so you can choose the magnetization model. So it can be relative permeability or it can be BH curve based. Okay, and the relative permeability as well can be, you can define it as user defined as well. So when we go to the magnet, so here you have the option to specify your magnetization model. So here in terms of remnant flux density, and here when we talk about the electric conductivity, so here anyway in this specific example it is not suitable, but based on your particular material and the application area of interest, in case if you want to incorporate anisotropy, so you can always define your material property to be user defined, and it usually you will have this option wherever it is applicable. So you can change to be user-defined conductivity. You can specify diagonal or fully anisotropic. So wherever it is applicable, so you would have the option to define the anisotropic material properties.
Thank you. We have a last question from Mr. Sanjeev. He says, how can we improve motor design or geometry of a part, and which type or parameter of simulation will give a better result?
Okay. So, yeah, when we are talking about parts, so you can always parameterize the part. So we right click, so you can load the parts from the part library. So once you load it, so you are going to just load a template, and this template is always parameterized. So when I call this template, this motor part to the geometry section, they are all parameterized, and these parameters you can write down the numbers, you can do a parametric sweep as well to assess the performance. And the next question was to understand which parameter will play a major role, etc. So that can be, one is through parametric sweep. So one is from a theoretical understanding. So which parameter is going to influence my result. The second understanding would be from the parametric study or the optimization study. And there is one another aspect called uncertainty quantification available within COMSOL. So the uncertainty quantification comes up with a study where you can assess which parameter influences your objective. So, which is the key influential parameter, so that can affect my result. So that is one more point of view that it can be thought of. But when multiple parameters are going to exist, so you can use that aspect as well to derive which parameter will highly influence your motor performance. But in general, a parametric sweep analysis as done here. So when you are going to do a parametric sweep as well, so you choose if the parametric sweep is going to be large and extensive, so you would choose this time periodic approach, so which will help you to do parametric analysis at a faster duration. I hope that answers
Thank you so much. Thank you so much, Ms. Kavita. So we don't have any more questions as of now. Well, as we come to the end of today's webinar, we extend our very sincere thanks to Ms. Kavita for sharing her expertise and valuable insights with us. The session has definitely provided an excellent overview of how simulation-driven engineering can support the design, analysis, and optimization of electric machines while addressing complex multiphysics challenges. I would like to thank COMSOL for their continued partnership and commitment to advancing engineering innovation through simulation and technology. And of course, thank you to all of our participants for joining us today and contributing to such an engaging session. And indeed, the recording of this session will be readily available on COMSOL website. So we hope today's discussion has provided you with practical knowledge and a deeper understanding of how multiphysics simulation can help address the challenges of modern electric machine design and development. So we look forward to welcoming you all again to future webinars and technical knowledge sessions hosted by eMobility Plus and First View Group. Thank you once again for your time and participation. Have a wonderful day.
Thank you, everyone from COMSOL and as well. Thank you.